That is, it's a cat. Look at you want to hear it. Mine is a stone. Yeah, why don't you want the stone? Literally.
We're going to prepare for our FRQ test, and this will be the Wednesday after we get back from break. So this is what your test will look like. It'll be front and back. It'll be table of values, basically a derivative graph, and just an assortment of different topics across AB, such as finding slope of tangent line, using chain rule, mean value theorem, extreme value theorem, curve sketching, U substitution. So just a lot of just a collection of a lot of AB topics into one problem. So, okay, so let's start off with reading the problem. It says let f and f prime be differentiable functions. So both f and f prime are going to be smooth curves. The table gives values of f and its derivative f prime as selected values of x. We have a g of x function that is given as sine of 3x minus e to the cosine 2x. H of x is some integral of j of t, and j of t is related to k of x. So these are connected. So part A, is there a value between 1 and 5 such that f double prime of c is equal to negative 3/4? So okay, so this is basically an application of mean value theorem, because we have data from f prime, right? We don't have f double prime in order to find that value, but we know that f double prime is the slope of f prime. So if I can show that the slope between 1 and 5 at the f prime level is equal to negative 3/4, then I can guarantee there must be a slope of negative 3/4 somewhere along this f prime graph. So if we think about mean value theorem, normally this is our formula, right? F of B minus F of A over B minus A is equal to F prime of C. But we can also adapt mean value theorem and just shift everything one derivative down, and it can still work. So if the slope of the f prime level is giving me negative 3/4, then I can guarantee that there must be a negative 3/4 somewhere along that curve. So let's test our points here. We'll test 1 and 5, 1 and for A, and 5 and for B. Nathan, do this one. Page 11. Okay. So f prime of 5. F prime of 1. So because the slope between the two endpoints is giving me a negative 3/4 at the f prime level, there must be an f double prime that is exactly negative 3/4, because the slope between the two endpoints is showing me negative 3/4. So yes, by mean value theorem, since f prime is continuous and differentiable, those are the conditions for mean value theorem, right? Continuous with brackets, differentiable with parentheses. There must be a point on the F. There must be a point where the second derivative must be equal to -3/4. So we're just applying mean value theorem, but just taking it one notch down. Okay. Part B. Let K be the function defined by K of X equals F of J of X. So this is a composite function here, function within a function. Write an equation for the line tangent to the graph of K at X equals 2. So to find tangent on the equation, we need order pair and we need a slope. So we can plug 2. And for X, use combination of the table and the function J of X to help us get to our order pair. And then to get to our slope, we got to get to our derivative. To get to our derivative, we have to go through what? What does that look like to you? Chain rule, right? Outside times inside derivative. Okay, so we'll just start gathering information. I'm sorry?
How do we get J?
So J of X is from this graph here.
Okay, sorry. So we don't like find an equation, we're just like taking the points.
Yeah, we're going to find order pair. We'll find K of 1, K of 2, and we'll find K prime of 2. J of 2 is just the order pair. J of 2 is at -1. And then F of -1, we can go back to our table and grab that value. So there's our order pair. Let's build our derivative to find our slope. So we said chain rule, right? Outside's derivative times inside's derivative. When we do outside's derivative, we keep the inside portion intact. And once we're completely finished with the outside portion, then in a separate space, we do inside's derivative. Okay, piece by piece, let's see if we can work our way down to getting a number out of this. So J of 2, again, is -1 times J prime 2. So F prime of -1, we go to our table to pull that value. It's -3. J prime of 2, we go to our graph here. Now this is J of X here. So how do I find J prime of 2? Slope, right? So find the slope of this line segment. down 2 over 1, so -2, right? Okay, part C, find the slope of the tangent to the graph of g at x equals pi. Similar process, we just now have a function that we're going to be working on here. So we actually are going to involve the derivative rules that we've gathered, that we've learned. So sine's derivative is cosine. E to the u is e to the u times u prime. And then cosine of u is sine of u times u prime. So let's build out g prime, and then we can plug pi in and get it down to a numeric answer. So different variations of chain rule here. We start off with sine of 3x. Go ahead and find the derivative of that. And then e to the cosine of u becomes e to the cosine of u times negative sine of u times u prime. Right? So nested chain rule with this e to the cosine of u here. E to the u becomes e to the u times u prime, and u prime is its own thing with cosine turning into sine of u times negative sine of u times u prime. Yeah, for each of just one. Just front and back, yeah. Just extended FRQ problem. Okay, so now we can replace all the x's with pi. Cosine of 3 pi, same thing as cosine of pi. Cosine of 2 pi is 1. E to the 1 is first, it's just e, but sine of 2 pi is 0, so it's going to wipe out this whole second portion there. Okay, next page. Oh, sorry, part D here. Any questions with part C? Okay, so part D, we have to move from h of x to h prime. So there's a little bit of second theorem involved here. So let's look at h of x first. And then let's build out h prime. So h prime is asking for the derivative of a function that has an integral notation in it. So we know there's going to be this second theorem process that's going to happen here. We know those operations cancel each other out. X gets inserted into the t, so just j of x. So if I want to find h of 4, just involving the area under the j graph. Now I want to read the graph. The graph is showing from my lower bound is higher than my upper bound, so I'm going to flip the bounds and change the sign. Use the j graph here. So let's find all the regions, the area of the shaded region here. So we have triangle, positive, triangle that's negative, and triangle that's positive. 1/2 base times height. See if you can find each of those regions. So this first region here is 0.75, 1/2 base times height. The second region here is 1/2 times 2.5 times -3, so -3.75. Third region here, 1/2 base times height, 1/2 2 times 3. I'm just looking from 4 to 6. 4 to 6 is going to be 3, but I flipped the bounds, changed the sign there, so -3. And since h prime is j of x, h prime of 4 simply j of 4, and j of 4 is just the order pair of my j graph, just the x-intercept, right? 0. I'm sorry.
Could we use a calculator?
Yeah, you'll get to use a calculator on the test.
The calculator to solve this problem.
I don't think we need to. We can just total the area using. Yeah, because we don't have a formula to plug in the calculator, unless you build one, but it's not worth the trouble, especially if they're geometric shapes. Okay, part E. On what interval is the H graph increasing and concave down? So we've already built the relationship that H prime is J of X, right? So we know that the J graph is the derivative of H. So we're basically looking at the H prime graph. So let's think about how we interpret a derivative graph. Above the x-axis is positive slope, below is negative slope. And then we know peaks and valleys represent the points of inflection of the H graph. And then positive slope of H prime would indicate where the original graph is experiencing concave up. This is concave down, concave up, concave down. So if I create a sine line, I can kind of see how my graph is behaving. So let me create my H prime sine line. So critical points at 1.5 and 4. Between 0 and 1.5, above the x-axis will translate to rising, positive slope. Below the x-axis, negative slope. And then from 4 to 6, positive slope. We can also gather our concavity information. We look for peaks and valleys, hills and valleys, max and mins. So 1, 3, and 5. Positive slope on my H prime is concave up. Negative slope is concave down. Positive slope, concave up. Negative slope, concave down. So now that we have everything lined up, it should be easy to spot where our original graph is going to be both increasing and concave down at the same time. Okay. What I meant to say is at the same time, not individually. So increasing and concave down. So basically needs to be above the x-axis and showing a negative slope. Also from 5 to 6. Okay, any questions? Okay, part F, find the absolute min, absolute max on the interval from 0 to 6. So for H. Now, anytime we look for absolute max, absolute min, that's an application of what? What theorem? Extreme value theorem. So extreme value theorem tells us to test what? Critical points and endpoints. So critical points and endpoints comes from your F prime, sorry, your derivative sine line. Don't look at your concavity sine line. That's not going to give you any information. So the only candidates that you're going to look for are from your slope sine line. So we'll test H of 0, H of 6, H of 1.5, and H of 4. They all get plugged into our definition for H. And then we can use our areas and displacement values to formulate the y values at each of those points. And then after we gather everything that we need to gather, compare our y values. Highest y value is your absolute max. Lowest is your absolute min. Okay, let's see if we can try that. I think we've already gathered all these regions, right? So my definition says from 6 to 0. So I always want to follow what the definition says. And after I have my definition written down, then I can decide that I want to flip the bounds if I want to make that adjustment. So I flip the bounds so that I can read from left to right so that everything is more straightforward. Above is positive, below is negative. And I just added up all my values, but -0 is still going to be 0. So next up, you'll test h of 1.5. Then you'll test h of 4. Then you'll test h of 6. H of 6 should be easy. What's nice about h of 6? Yeah, the balance is going to be just the same. So you know that's going to be 0. And we already found h of 4. So just h of 1.5, that needs to be done. Any questions up to part F? Part G. The integral of f double prime of 2x. Now we see 2x inside a set of parentheses there, so we have to go through a little bit of what? Chain rule. Not chain rule, but use substitution, yeah. Let me just give another minute if anyone wants to catch up. I also have the key attached to your packet, so. So here's the big picture, right? We know that the integral from a to b of f double prime of u is going to eventually turn into what? What does first theorem tell us? F prime, right? And then F prime, I can just plug in my upper and lower bound, right? So that's our ultimate goal. We know that we're just applying first theorem there, but we want to get that 2x accounted for. So we'll go through use substitution so that we can take care of that 2x there.
And we just put the values in and multiply by 2 and we put it in.
It's not the same. Yeah. Yeah, that 2x is causing it's like saying the integral of sine of 2x, right? We have to go through use substitution if it was this problem. We'll have to use substitution for this problem as well. Okay, so get everything in terms of u, pull the 1/2 out in front. So now we have that inside 2x accounted for. We can go through first theorem. 1/2 f prime of u. But right now, it's still incompatible, right? We have the antiderivative, but our bound is in terms of x, but our antiderivative is in terms of u. So I would bring the x back in and then plug in your upper and lower bound. Okay, we made it go through the calculus procedure here, antiderivative. And then now we can plug in our upper lower bound once we get our variables to match. We look to see if we can get these values down to numeric values or function notation into numeric values because we have our table of values in front of us, above us. So f prime of 6 is 2. F prime of 2 is 3. Okay, let's go to page 16. Okay, a sand pit is being filled with sand whose height at any time is given by a differentiable function. So we know h of t is smooth curve. H prime is also a differentiable function. Represents the rate at which the height of the sand pit grows in inches per minute. It is known that h prime is increasing on the entire domain. The height of the sand pile is 40 inches at 9 minutes. Estimate h double prime of 2. So we don't have a function to find the derivative, but it says estimation, so we can just rely on what? What's the algebraic version of a derivative? Nice. But we're already at the h prime level, so just find the what? But we don't have a function to find the derivative, so slope, yeah. So what points would you choose if you want to estimate h double prime of 2? Yeah, 1. What's our unit of measure going to be if h prime is inches per minute? Yeah, inches per minute squared.
And you could take the graph, solve for UI dx.
Well, we don't have a function to work with. All we have is budget border pairs. So it's only asking us to estimate the rate of change at 2. And the rate of change of 2 is just the slope between the two endpoints. Right. H double prime of 2 ends up giving us 3 halves. So the way we can interpret it is we'd want to use the word acceleration. We want to say the rate is increasing, right? The rate of the height change is increasing at 3/2 inches or 1.5 inches per minute squared. Okay, part B, use Wright-Riemann sum. So we want 4 subintervals because we have that number of order pairs. Or we can create 4 subintervals. Identify the width of each subinterval, pull the correct height that we want because it's a right Riemann sum. And when we take the integral, or if we talk about the integral of h prime, what is our unit going to be then? Yeah, inches, right? So this will tell us, how much sand has been filling up into the pit in that time period. Or how much change has occurred in that 12-minute period, right? 84, because if we keep accumulating sand over that time period, then that accumulation of that rate is going to give us how much sand has been added to the pit. Okay, part D. Include units, evaluate the interval from 0 to 9 of h double prime. Well, we know that this is basically using first theorem. We know h double prime is going to rise up to h prime, plugging the upper and lower bounds. Our units will be back to inches per minute. All right, your homework is just to finish up page 16 and 17. And I also want to check pages 11 and 12. We did it in class, but just want to give you credit for that as well. So I'll send out a reminder this afternoon. The key is attached to the back of these pages there. All right, can we get your phones?
What is that? What is that from the yo? Erase that. Yo.
Not gonna.
No, you had it.
I do James, you do it.
Oh,
Thank you. Homework. Page 11, 12, 16, 17.
it's gonna put an Instagram on this.
Yo, Daniel.
Not like
He added something.
very. Oh, you said. Yo, if you have also if you have like a let's play open thing that over the I think there's you had it on the website, right?
Yeah. If you can finish off this packet, have you had a chance to watch videos yet? Did you see the text?
Let's play ultimate tic-tac-toe.
Oh, yeah, I saw. No,
Watch that. Okay, so.
yeah, yeah, sorry. I did something.
Dance your double log.
Okay, yeah, so, yeah, work through this packet. I can also give you the next packet if you want to start looking at it.
Yeah.
Yeah, so yeah, just work through the packet. I have all the videos from last week.
I'm ready.
It's Joe.
It's just like a review of the whole.
Yeah, it's just this and a bunch of FRQs. That's it.
For second 12th, no recommendation for kids. So instead to let you know that you teach. No, I'm
Yeah.
I'm gonna rip it over.
yeah. Okay, I have next.
So that,
I wanted
Yeah.
to put in your last name.
Oh, got it.
Yeah.
I'll just text
Yeah,
you.
this part where it says my social security.
Oh, okay, you're right.
No, I said I think it's next first.
Yeah. This is right there on my school.
Yeah, third
Thank you.
question.
It's gonna be what means like exactly kind of.
I don't memorize the
Like
meter stick. Oh, I know what you're
yeah.
non-uniform.
Yeah, it was.
Let me see. Yeah, I haven't printed it out yet, but I'll try to print it out today. Tomorrow. Are you here tomorrow? Okay, all right.
Oh,
Yo,
oh, yeah, I just did, I just did the center of mass forming. Like, I just use that, so.